In the last video, we defined the definite integral, but we never tied it to the indefinite integral nor to antiderivatives. And that's what we're going to do in this and the part 2, the follow-up to this video. So we're going to look at the fundamental theorem of calculus, part 1. And obviously, if it's the fundamental theorem of calculus, it's pretty important. This is what ties calculus all together. This is what makes it all work. So if f is a continuous function on the closed interval a to b, then big F of x is equal to the integral from a to x, little f of t dt, is continuous on the interval a to b and differentiable on the interior a to b, and its derivative little f of x is equal to big F of x primed, which is equal to the derivative of that integral. So tying together, like I said, the derivatives and the antiderivatives into this definite integral. If we want to find, if we take the derivative of an integral, taking the derivative of that antiderivative gets us back to that initial function, just perhaps with a different variable. So let's take a look at what I mean with that different variable in there, and let's just see how it all works. Let's find dy dx for y equal the integral from a to x of 2t dt. So we're starting with this one equation, y equals an integral. Currently that function is in terms of t, the independent variable t, but we're integrating out to a variable x. We want to find the derivative of this thing. So I'm going to ignore this fundamental theorem for right now. I'm just going to treat this kind of like what we've been doing in terms of the antiderivative. So if I wanted the antiderivative of 2t, I'll call it big Y. Well, big Y of 2t would be equal to t squared plus some value of c. Now I'd have to evaluate at the x and the a. And here's the thing with that c. That c really just doesn't matter. And we're going to see why that is. So if I'm going to evaluate between the x and the a and the x, that means I'm going to have to find out what both of their values are. If I think about this line, right? Know what the line looks like. We want to know the area underneath between some value a and some value x. So I need to find the value of that x and subtract off the value of a. So the y value would be equal to x squared plus c minus the a squared plus c. We've found the value of this function at the larger value, and we're subtracting off the value at the smaller value to figure out how much is actually in the middle here. And so we can see that these c's disappear. And so we're left with x squared minus a squared. And then what the dy dx tells us to do is immediately come back and differentiate this. So we want to know the derivative of x squared minus a squared. Well, a squared is just a constant, so the derivative of x squared is 2x. And that's our answer. And this big theorem here, this long theorem, just tells us that if we're taking the derivative of an antiderivative of this definite integral, it has to just leave us with that original function, the original function just being the 2t, but we had to differentiate it with respect to x. So let's do this problem faster. Let's do a slightly different problem, but faster. Find dy dx for y is equal to the integral from 2 to x of 19 x squared plus 5 sine x. They should be t's. Let me go back and fix those because right now there should be a different variable if we're going to integrate with respect to x. So 5t squared plus 5 sine t times cosine t minus 1 dt. Well, I don't want to have to integrate that function even if I did know how to integrate it. And so because all we're doing is we're taking the derivative of an integral, that means they should be canceling out. So we're going to take the derivative of the integral from 2 to x, 2 to x of the 19 t squared plus 5 sine cosine minus 1. And so the fundamental theorem of calculus says the only thing we need to go back and switch here are those t's are going to become x's because we're differentiating out to an x. And that would be my answer. So make it a little bit harder still. Let's do another example. Let's find dy dx for y equals the integral from 2 to x squared of 3t dt. Well, the reason this one's a little bit more complex is because I know that if I take the derivative of the integral, it should give me back to the original function, as long as I'm integrating just to the function x, as long as we're integrating to that single variable. But the problem is, here we'd have to do the antiderivative, and the same way we did on that first one, we'd plug in a x squared, so we've changed the variable. And so we'd have, at some point, 3 times x squared. Well, now that has an inner function to it. And so when I go back to take the derivative of this thing, I'm going to have to apply a chain rule. And so let's break this down a little bit more. I need that variable sitting on top just to be a simple function. So what I'm going to do for just a second is I'm going to call y, the integral from 2 to, I'll say, u of 3t dt. Now, if I asked for dy du, that would be very simple. We'd just say, well, it's 3u. Problem is, we didn't want dy du, we wanted dy dx. But we said that we'd have to use a chain rule here. So let's think about what the chain rule tells us. Dy dx, if we're going to take the derivative of y with respect to some variable x, but there's some sort of chain in between, we can take the derivative of that y with respect to the intermediate variable, but then we have to multiply it by the derivative of that inner function. In this case, what we'd be needing to look for is du dx. So coming back up here to my green work, we found the dy du. We replaced that u, and let's think about what we replaced u to be. U is really an x squared. So like I said, if we'd integrated this, we would have ended up as an x squared as an inner function. Well, we need to take the derivative of that inner function, and that would be 2x. And so now we can put these pieces together. The derivative of my outer function would have just been the 3u that we would have expected, or 3 times the variable that we expected. The derivative of the inner function we found to be the 2x. Now u is just a made-up figment of my imagination to make this problem a little bit easier. It wasn't actually there to begin with. So what I need to do is I need to go back and make sure I replace that u with what it actually was. U was x squared. And so when I multiply all these together, I get a 6x cubed. So if we have a function inside the upper or lower bounds for those integrals, we're going to have to still treat this as a chain rule. Let's do one more with that idea. Let's find dy dx for y equals the integral negative, let's go with e to the x to 4 of sine t dt. Well, once again, I see that I have that variable in my bounds, and that's one problem. And the other problem is it's in my it's in the wrong order. We're not integrating from the constant to the variable like we need to be. So I'm going to switch some things around here. I'm going to say let's y will equal integral from 4 to, and let's just go ahead and replace that with a u while we're at it. But if I'm going to switch these two integral bounds, I need to put the negative in front. Sine t dt. And so now if I take the derivative of that y, we're taking it with respect to u, we'd get a negative sine t, sine of u, because I need to keep my variables straight. We're taking the derivative with respect to u, so the variable becomes u, and the negative follows down because of the constant multiple rule. But we also had here, we let u equal negative e to the x. So I have to think about what the derivative of that inner function would be. And the derivative of negative e to the x would be a negative e to the x. It happens to be the same because it's the exponential function. And so now we can put this all together. Dy dx would be equal to the derivative of the outer function, negative sine u, times the derivative of the negative e to the x, the inner function. I need to do a couple things here. I'm going to simplify by multiplying with negatives, and I'm also going to replace that u with what u was, negative e to the x times e to the x. And there would be my equation. So that's the first of our fundamental theorems. The next will allow us to actually calculate those definite intervals.